Hello, my name is Paul Ghanem. I'm a PhD student at Northeastern University, and I work in Silicon Synapse Lab. Today I'm going to discuss my paper, Fast Estimation of Morphing Wing Flight Dynamics using Neural Networks and Cubature Rules. First, we begin with the introduction to elaborate on the background, motivation, and problem statement and goals. Our lab at Northeastern University has developed a small and lightweight flapping wing robot. It has a bio-inspired arm wing mechanism. It's small and lightweight, it's soft, and it has soft and rigid computational structure, and its wing expands and retracts during flapping. Identifying aerodynamic forces acting on the robot is very challenging due to its different gaits and modes of flapping. The goal of this work is to learn these aerodynamic forces acting on the wing and learn aerodynamic forces when the robot is in different configuration. In this slide, we will explain the dynamic wing morphing that we observe in bats and our robot, which is designed to mimic some of these capabilities. A biological robot has 46 modes of flapping. Our robot mimics just two modes of flapping, which are the upstroke and the downstroke. The upstroke makes the wings go up, and during the downstroke, the wings go down. The upstroke and downstroke is generated by the motion of the crank, which oscillates periodically according to a periodic input. When the crank oscillates periodically, it generates flapping motion of the wing using our computational structure. In this work, we combine neural networks with Cubature rules to learn aerodynamic forces acting on the robot. We use tools from physics-informed neural networks and Cubature-Kalman filter to design a recursive algorithm that trains neural networks using Cubature rules. We build on top of previous work which designed the robot by Ramazani, physics-informed neural networks by Raisi, and Simon Hyken's Cubature-Kalman filter. Our presentation is outlined as follows. First, we describe the morphing microaerial vehicle model. Second, I go through the aerodynamic forces learning methodology. Then I explain the Cubature rule approximation used in this methodology. And then we proceed to conclusions and future work. The dynamic modeling of the robot is done using the Euler-Lagrangian method. The full dynamic equation of motion, which are the original equation of motion of the robot derived in the original work, are described in the upper left slide, at the upper left side of the slide. So U1 represents external control inputs, U2 represents external aerodynamic contribution, B1 and B2 are the maps of the control input and aerodynamic forces to the state space. F of x is the intrinsic dynamic of the aerobat derived using Euler-Lagrangian method. We observe y, which is the wing flapping trajectories, which is usually the states of the robot. To model these aerodynamic forces, specifically B2, U2, we use a neural network. We replace in the hybrid state space equation the aerodynamic forces by a neural network, and therefore the state space would be augmented to include the neural network weights W. W are assumed stationary, which means their time derivatives is equal to 0. This is because to train the neural network, we have to drive these neural network weights to their optimal value, and their optimal value is a constant. We use the trajectory y, which includes the states and their time derivative, to calculate the aerodynamic forces phi, as we will describe in the next slides. The network that we used is a 20-unit single-layer neural network followed by a tanh activation function. The aerodynamic forces action mechanism is explained here. The wing expands and retracts in one flapping gait. Each wing is divided into distal wing segment, which is highlighted in the figure 3 as the dark yellow segment. In each segment, the aerodynamic forces U act on the application point P on the segment to produce the aerodynamic forces which are mapped to the state space. In this slide, I will describe our learning methodology. As I said, we augment the state space to include neural network weights at time k, wk, and we assume these neural network weights have a Gaussian distribution with mean w at time k. The neural net output at time k is ak. Our goal is to learn w hat, where the learned neural networks is given by a hat. To train the network, we use our measurement y and our partial knowledge of the model to get the empirical value of the aerodynamic forces acting on the robot. With measurement x, the training data is obtained, is described how it's obtained at the upper left side of the slide. B2U2 is y minus f plus B1U1. Then we store this empirical value of the aerodynamic forces at time k and ak, and we have to find the value of the weights given all the past data from A1 to AK, which we store in the big vector AK. Our goal is starting from known value, initial value of WK given AK to determine the probability distribution of WK plus 1 given AK plus 1. So we use Bayes' rule to develop to get like a theoretical value of PWK plus 1 given AK plus 1. And then we solve this posterior using Cubature rules. When we solve this posterior using Cubature rules, it results in the following update law, where W hat at time k plus 1 is equal to W hat at time k, which are the neural network weights, plus a Kalman gain k times the error. Just to clarify one thing, the W are the neural network weights, and they are treated as a random value, that has a mean and standard deviation, mean and covariance, and that's assumed to be Gaussian. X is the aerobite joint angle and positions. X dot is its time derivative. Phi is a neural network, and we assume that the neural network weight have zero mean Gaussian noise nu k, and the neural network output has a zero mean Gaussian noise r. So as I said in the previous slide, our goal is to approximate, is to get the posterior approximation PWK plus 1 given AK plus 1, starting off known PWK given AK. PWK given AK is a Gaussian random variable with mean W hat k, which is the estimated value of the neural network weights at time k. Here I will just describe finding just one probability distribution that constitute the posterior, which is the conditional distribution PWK plus 1 given k given AK. The mean of the distribution W hat k plus 1 given k is the integral of the weights at time k times the probability distribution. Similarly, in similar fashion, its covariance is also an integral with of the weights times the probability distribution of WK. Solving these integrals analytically is computationally infeasible, so we ought to solve these integrals using Cubature rules. On the upper left hand side of the slide, the Cubature rule approximation of the integral of the form given above is given by the summation of evaluation of Cubature rules, by the average of functional evaluation of these Cubature points. M is a sample number. Let's say we pick M Cubature points, we evaluate the average of M Cubature points, and then we get the approximation of the integral. This Cubature rule approximation is used in the derivation of the Cubature-Kalman filter by Simon Heiken that I cited in past work. So the posterior probability PWK plus 1 given AK plus 1 is given by the following formula in the upper right side of the slide. All distribution of this equation on the right hand side are solved using the Cubature rule approximation, and if you find the mean and covariance of each of these distribution, you can get the mean and the covariance of the left hand side probability distribution, and therefore the mean of the left hand side probability distribution is the next value of the neural network weights, and therefore the update law becomes w hat k plus 1 equals to w hat plus a gain times the error, which is obtained by solving the posterior above using Cubature rule approximation. We summarize this Cubature rule approximation algorithm in algorithm 1, where we start with a known initial covariance pk given k and initial known weights wk given k, which in our case would be w0 if we don't know the weights, and we start with an unknown also covariance, and then we apply this algorithm recursively until the weights stabilize and we reach a final value of w hat. In summary, we use the recursive Cubature sampling to find mean and covariance of the posterior. The neural network weights are updated every 1 second in an online fashion, which we will describe in the following simulation. In our simulation experiment, we combine algorithmic differentiation with our recursive algorithm to produce faster computation. For this reason, we use a toolbox called CDC, which has great success in path planning and motion control and robot manipulators. Usually, classic dynamic computation method is done using MATLAB symbolic toolbox. So you usually calculate the Coriolis and gravity and the inertial matrices using MATLAB symbolic toolbox. However, CDC has proven to be accurate and by an order of magnitude faster than MATLAB symbolic toolbox. So for this reason, we combine it with our algorithm, which and we show that CDC has much faster execution time in figure 5 and 6 for executing Coriolis, gravity, inertial matrices, and the execution also of aerodynamic forces. We tested our algorithm in simulation, where figure 7 shows simulation results. The ground truth of the aerodynamic forces is presented in blue, and the learned aerodynamic forces acting on the robot is presented in red. The left-hand side presents the aerodynamic forces acting on XYZ direction of the robot, and the right-hand side presents the aerodynamic forces acting on the 4 joint angles of the left wing. So these results represent training represent testing of the robot when it's in different flapping gaits. So when there is a stable gait, the signal doesn't change much, and the learned signal shows stable learning. Nevertheless, when there is a change in the gait, when there is an abrupt change in the gait, the signal shows that the algorithm shows that it can adapt with this change, and the learned signal adjusts with this change due to the recursive nature of our algorithm. So the weights are updated when the gait is changing. As I said, ideally the weights should converge to a stationary value. So the optimal weight should converge to a constant value. Therefore, to measure convergence of our algorithm, we measure the norm of wk plus 1 minus wk at each time step k of the vector of the weights. And this norm, we show that the norm of the weights, the norm of the difference of the weights stabilizes around 0. It keeps oscillating, but it reaches a very small value, which means the weight stabilizes, which shows the success of learning the optimal weight. So in summary, we used recursive Cubature sampling to find mean and covariance of the posterior of neural network weights. Neural network weights are updated every 1 second in a line fashion according to the recursive algorithm that is derived by approximating the posterior at each time step k. The weights stabilize with time and do approach the optimal weight. In conclusion, we employed the neural networks and Cubature rules to learn inertial and fluidic forces acting on a morphing microaerial vehicle called Aerobat. The neural network design extends to prior work on Bayesian filters, which is the Cubature-Kalman filter. We used Cubature rules using the Cubature-Kalman filter to compute Gaussian-weighted integral efficiently and recursively, resulting in a recursive online algorithm capable of accurately learning multi-degrees of freedom aerodynamic forces of morphing microaerial vehicles. In our future work, we will focus on implementing the learning method on the actual robot with real data, but this is pending installation of joint encoders on the robot. Finally, thank you for listening for this presentation. I did wish to be in CDC, but due to unforeseen visa issues, I could not make it. So I do wish if I could be there and listen to your questions and the feedback, but thank you for listening.